Obtaining a micrograph of a sample involves 5 steps of preparation. We're going to walk you through the process to give you an idea of how sample prep is done. The first step of the process is sectioning. The saw used depends on the composition and the size of the sample you have. The diamond cutoff saw is used for small samples that require small, precise cuts. The first step is to tighten the blade onto the machine. And notice the safety shields aren't on, just for video purposes. And notice the sample is in the saw arm, which is now being lowered. Turn the blade on and wait for the sample to be cut. Turn the blade off when it's cut through, and there's your sample. The silicon carbide cutoff saw has a thicker blade and can be used for larger samples.
This sample is an aluminum bronze ingot. Make sure when you put the sample in the saw that it's completely tightened down, otherwise it will wiggle itself loose and end up breaking the saw blade, which is not cool. So for this saw you have to turn on the water because the saw blade will heat up when you're cutting, and that could possibly cause microstructural changes. And here I'm moving the table into the saw blade. You can also operate this saw by pulling the blade down onto the sample. So here you have the finished cut. And there's your sample.
Grinding on a belt sander is done to flatten the sample and to remove sharp edges and large scratches caused by the saw.
Here's the sample we just cut. So you start by turning on the machine and the coolant water. Here we're increasing the flow. And you just place the sample on the belt sander. Here we have a sample that has a bevel. That's not good because it will obscure the micrographs that you would like to take in the end. So you just hold the sample on the belt sander, keeping it as level as possible. It can take a while. And here we go. We have a nice smooth finish, and we will be able to polish the sample.
Large samples are easy to hold, but small samples need to be mounted. There are 2 types of mounting processes we'll cover. Hot mounting, usually done with bakelite, is used for samples that can withstand heat and pressure without changing the microstructure.
This is the section of the ingot that we just cut. The sample that we cut with the diamond saw is too small to hold on a belt sander, so we have to mount it in bakelite. Here it's getting lowered into the machine. This is powdered bakelite. It is a polymer and will polymerize when you apply heat and pressure. So to start the process, you close the machine and then you just hit the start button. This process takes a while, about 15 minutes, and when you're done, you will have a nice sample mounted in bakelite. Here's the sample as it comes out of the machine. It's quite hot, and as you can see here, our sample is partially obscured by the bakelite, and the edges are somewhat sharp. So we must grind it down on the belt sander. Pretty much the same process as with the aluminum brass ingot. Make sure you round the edges to get rid of any sharp edges, and then grind off until the whole sample is exposed, like this.
Cold mounting, often done with an epoxy resin, is used for samples that can't withstand heat and pressure, such as brittle or porous samples. The epoxy resin is mixed by weight using a scale. So here I'm going to zero out the scale. And the resin is 25 grams. And the hardener is 3 grams. once that's weighed out, you're going to stir it very thoroughly for about 3 or 4 minutes. And this is a piece of slag, which is very porous and brittle, so it can't be mounted in bakelite. One edge is flattened so that it'll sit flat in the mount. And you place the sample in the little holder. This is the same type of sample. And pour the epoxy in the 2 containers. And vacuum infiltration is done to remove air bubbles and fill any pores. It's only done with cold mounting. Vacuum infiltration is done for porous samples to get rid of any air bubbles from pouring the epoxy and to even out the epoxy in the small containers. The lid of the vacuum chamber is particularly hard to get off, as you can see. You place the samples into the compartment, put the lid on, and here you can see the air bubbles rising to the surface and popping, and this is after about 10 minutes of vacuum where there's no more bubbles and the epoxy is very clear. This particular epoxy sets in about 12 hours. This is a finished epoxy sample with beveled edges. Polishing a sample is done to get a smooth mirror finish. The basic idea is to start on a wheel with large particles and work down to smaller and smaller particle sizes. This is a native copper sample. You can see it's particularly scratched and needs polishing. We're going to start on the 320 grit, which is the coarsest we have. I put the water on so it doesn't heat up and place the sample on the wheel. You can see you can use 2 hands or 1 hand, whichever's comfortable. You'd normally hold it on the wheel for about a minute or 2. Always rinse the sample between each wheel and check under the microscope to see that all the scratches are uniform and only from the 320 grit. Now you move to the 400 grit, which is slightly finer. Turn the water off, put the lids on, rinse it off. Now you can see that the sample is slightly less scratched and a little bit more shiny.
You repeat this process for the 600 and 800 grit wheels. After finishing the 800 grit wheel, you move on to the diamond wheels. You have to use oil on these wheels because the diamond paste shown here is water soluble. This is the 6 micron diamond wheel. How it works is you apply the diamond paste directly to the wheel and then you add oil for lubricant. You apply the oil on the wheel, and then you start the wheel spinning and put the sample down. For the diamond wheels, you don't hold it in one place as you would for the silicon carbide wheel. You move it counter the direction of rotation of the polishing wheel. You add more oil if necessary. And for the oil, you have to rinse it off with soapy water. To make sure your sample's clean, you'll have to rinse again after the next diamond step as well. So this is the 3 micron diamond wheel. It works the exact same way as the 6 micron diamond wheel, except you have to use the smaller paste. So here we are putting the oil on the wheel. And again, moving it opposite the direction of the wheel rotation.
The next wheel is the 0.05 micron aluminum oxide, or alumina. For this wheel, you shake a bottle of water and alumina particles and apply it directly to the wheel. Again, we're not using any water on this wheel. And again, you move the sample counter to the rotation of the wheel, or for soft samples, you can hold it in one spot. The sample then needs to be rinsed with isopropyl alcohol or ethanol to remove all the alumina particles.
For most samples, the alumina will be your final polishing step, but soft samples may require colloidal silica. It has a pH of 9 to 10, so it may etch your sample. When you're done polishing, you'll have a nice mirror finish.
Chemical etching is done to reveal the microstructure of a sample. Etchants remove material from the grains or grain boundaries, depending on the etchant used.
Different materials require different etchants. We have a large collection of etchants in our fume hood as shown here. For a ferrous sample you would want to use nitol, but brass, like what we're etching here, takes a different etchant. Once you swab the etchant onto the material, you have to rinse all the etchant off to stop the etching process, otherwise your sample will be over-etched. If you do not etch it long enough, then it will be under-etched and will obscure the microstructure. So once you're done, you should have a nice polished sample, and you'll have contrast so that you can see the microstructure of the material.
Microscopes are used to observe the microstructure of the polished and etched sample. Most microscopes have a real-time camera attached to them, so you can see what you're doing. And on the computer, you can alter the image settings to make the image look as good as possible. If you need to see something in more detail, you can increase the magnification, as you can see here. There are a few characteristic microstructures, and we'll show you 3 here. In a typical cold work structure, such as this cold hammered copper, the grains are elongated in one direction. This is a bright field image, and in bright field imaging, the grains appear bright, while the grain boundaries look dark.
Cold work samples can be annealed. The annealed microstructure has equiaxed grains, meaning that they are relatively circular. In dark field imaging, the grain boundaries appear bright, but the grains appear dark, the opposite of bright field imaging. Dendrites are observed in cast microstructures and are fern-like in appearance. They start at the outside of the sample and grow inward as the sample solidifies, exhibiting a preferred orientation. As a result of phase separation, there are 2 phases in this brass sample.